Alright, now we want to have a look at how we can expand that definition to work with many more data cases or a larger set of data. So if we took our histogram, and this is a histogram of the masses of members joining a Toowong branch of a popular weight loss program, if we actually joined the midpoints of each bar, we would get what we call a frequency polygon. And you would have done frequency polygons in grade 10. Okay. But you'll notice that on this frequency polygon over here, these little lines are quite distinct from each other, and so you can actually see the gradients of them. But if we didn't only have 40 people joining, what if we had like 4,000 or 40,000 people joining? Our intervals would be smaller and smaller and smaller, and so our little lines would be really short. And what we would end up with when we join all the center points is we would actually have a smooth curve. Okay. And once we've got a smooth curve, we can actually start using some of the techniques that we've learnt about before. So it's possible to develop a function, f of x, to model that curve, and that's actually going to give us the approximate relative frequency or our probability values. And for our weight loss program, 38% of the area under the curve is bounded by the x-axis and the line x equals 84. So that then shows us that the relative frequency of members having a mass of 84 or less, or our probability of x being less than 84, is actually 0.38. Now, hopefully, having talked about areas under curves, that's made you think, I know how to calculate an area under a curve, because we've actually learned how to do that, because we can actually integrate. Okay, so the absolute area bounded by the curve in the x-axis can have any value greater than 0. Okay, but to make things a whole lot easier for us, we actually scale it down so that our total area under the curve is equal to 1. And then it gets called a very special thing. It's actually called a probability density function. Probability density function, or a PDF, for that continuous random variable. Okay, so using calculus, the probability that a continuous random variable x lies between the values of a and b is given by, and we've got our probability there, it's our integral from a to b of f of x dx. And what we're really interested in here is this percentage of area under the curve. Okay, now using that definition of the integral, it actually helps us to understand why we can't get an exact value for a probability, or a probability at a point. Because if we then integrate from x to x, we know that we would have our integrated function from x to x, and we know that would then be f of x minus f of x, which is actually 0. So therefore we can say that our probability of x equaling x, taking on an exact value, is equal to 0. So no exact values. There'll always be intervals. Okay, now this is kind of similar to discrete random variables, but you need to keep them apart in your head. So let's have a look at our definitions for discrete random variables. Remember that for discrete variables, our probability values took on values between 0 and 1. They had to be positive numbers between 0 and 1. For a continuous variable, our our function cannot be negative. So it has to be a positive function, it has to be above your x-axis. Okay. For discrete variables, remember the sum of all of our probabilities had to equal 1. And for continuous random variables, because we've got a probability density function where it's scaled down so that our total area is equal to 1, our integral between a and b of our function has to equal 1.